The mole, Avogadro's number. What is it? Where does it come from? And how do we use it in chemistry? So I know that personally, I always found fully understanding the mole very difficult. So I'm going to try and go step by step, slowly through this video to make sure that you really grasp this concept. Okay, so the purpose of the mole is just a number. Okay, this is the mole here, this number, this really big number. And what this number does for us is it allows us to connect masses and counts of atomic-sized particles. So electrons, protons, atoms, molecules, atomic-sized particles, masses and counts. At the atomic size level, we can connect with masses and counts at the macro size level, so the human size scale. That is the entire purpose of the mole. We have scales that can measure weights in grams or milligrams or pounds, right? Macro scale, human scale measurements that our instruments can measure. Well, with the mole, we can connect a certain amount of grams of a substance or pounds of a substance or whatever units you can think of that a scale would measure with the corresponding masses of the atomic-sized particles in that substance. And even with counts, instead of having to think about a count, that this huge number, enormous number as far as the number of atomic-sized particles you're dealing with, again, protons, electrons, atoms, molecules, we can bring that number down to a more reasonable size, like regular integers, whole numbers, 1, 2, 3, 10, 9.5, etc. Okay, but how exactly does this work? What is this number? Does it have units? Where does it come from? And how do we use this number to connect with the atomic-sized measurements? Okay, well, we want to start by thinking about how in the 1800s, when atomic theory really gained traction, and they were discovering elements and organizing the elements, creating the periodic table, and trying to analyze properties of elements. Okay, when I say elements, I'm referring to, properties of atoms, right? If you're analyzing elements, you're analyzing the atoms, the isotopes of the different elements, or just the group of isotopes all mixed together within one element. So what they're also trying to do is analyze properties of these elements, of these atoms. And one property would be the mass. So what's the mass of carbon or oxygen or sodium, right? Well, you can imagine at the time, and still today actually, this is very difficult and actually even currently can't be done from the perspective of just a single atom at a time. Like in the 1800s and even still today, we can't take a single carbon atom and you could think about like put it on a scale and see how much it weighs or what its mass is, because atoms are way too small for us to work with them in that way. Or furthermore, even if we could think about actually somehow picking up a carbon atom, well, how are we going to put it on a scale? How are we going to have a scale calibrated to weigh a nitrogen, a certain isotope of nitrogen, right? But the next best option then, what they were able to do in the 1800s and what we are able to do today at an even higher level of precision than it was done in the 1800s, is we can determine relative masses between atoms or any atomic-sized particle, between atoms or electrons or molecules, whatever. Okay, relative masses. And this is done using mass spectrometry. So this is a diagram of, like a simplified diagram of one type of mass spectrometer. Here you have a gas sample that comes into this there's a vacuum pulled in this tube here. And then the gas sample is bombarded with a stream of electrons, high energy electrons. Then collisions between the electrons and the gas sample produce positive ions by dislodging an electron from each atom or molecule. But what you can think about is the mass of electrons, as we've talked about, are significantly like 2,000 times smaller than just the mass of a single proton or neutron, but with atoms, you'll have multiple protons and neutrons, so just losing a single electron is a tiny percentage of that entire atom's weight. So you effectively have the same mass of atoms coming in here as you did with the sample gas. But even then, you could still potentially, since you know you just lost a single electron, you could apply some correction factors to the final results to add in the lost electron if you wanted. Okay, so then these positive ions are accelerated by these charged plates through this magnetic field here, which deflects the charged particles onto this detecting screen. And the degree of the deflection, the radius you could think about of the deflection based on the position on the detecting screen, when you compare these degrees of deflection, you're going to have like a higher degree of deflection for a lighter atom. So you can use calculations based on the positions shown on the detecting screen to determine relative masses. So a relative mass would be like, for example, you might say something like a certain isotope of fluorine. So let's say fluorine 18, 9 protons, 9 neutrons, has a mass that is, I'm just throwing numbers out here, but let's say 4.5 times larger than the helium-4 isotope. Or you might say that a certain isotope of titanium is, let's say, 0.6 times the mass of krypton. That's the idea of determining relative masses between atomic-sized particles. Again, atomic-sized particles, it's not just atoms. It could be anything. You could say, well, look, a proton is about a fourth of the mass of the helium-4 isotope, right? Or you could do this with molecules, whatever. Okay, and so now to make it easier to communicate relative masses between atomic-sized particles, what you want to do is define a new unit of mass. Okay, a unit it's something that you assign a value of 1 to. Okay, and then from there, quantities of you can take all kinds of quantity measurements and represent them as relative to what you define to be 1. So masses at the atomic size scale, the internationally agreed upon unit for masses at the atomic size scale is the AMU, or the atomic mass unit. Okay? And the definition of the atomic mass unit, the definition is based on the carbon-12 isotope, so the specific isotope of carbon that has mass number 12, so since all carbon atoms are going to have 6 protons, that means this isotope is going to have 6 neutrons in the nucleus. Okay? And the definition of the AMU is, the AMU is, so 1 AMU is equal to 1/12 the mass of a carbon-12 atom. This is a definition, so that this is exact. 1 AMU is exactly, by definition, equal to 1/12 the mass of a carbon-12 atom. Okay, and so what you can see is that with this new unit defined, now when you're taking relative masses, when you're determining relative masses between atomic-sized particles, you don't have to keep saying, okay, well, this atom weighed 6 times more than this other atom, and then this other atom weighed 12 times more than this other atom, and you're constantly having to keep track of what weighed more than what and by how much. No, you can express everything in AMU. You could do a measurement and say, okay, let's compare let's do a relative mass measurement between carbon-12 and sulfur, a certain isotope of sulfur. And if you determine that this certain isotope of sulfur is, I'm just throwing out numbers again, 10 times the mass of carbon-12, well, then you can easily express that in AMU. If something has a mass that's 10 times the mass of carbon-12, well, if carbon-12 weighs 12 AMU, then that, whatever you took the mass of, is going to be 120 AMU, right? Okay, but however, note, though, that based on everything I've talked about so far, the AMU, the definition of the AMU at the moment is a little bit different from the definition of, say, something like the meter or the pound, because with those kinds of definitions, we have a direct reference of, okay, this is how much a pound weighs. I can hold a pound in my hand. I can look at a meter, like a meter stick or whatever not a meter stick, that's calibrated in terms of the meter, but whatever the meter is defined to be, I can look at an example of it. I can hold a pound in my hand. I can have direct references, physical references that I can visualize this unit with respect to. At the moment, the AMU is mysterious. In the 1800s, if all you're doing is strictly, you only have the ability to compare, to look at, to determine relative masses between atomic-sized particles, well, then you really don't understand what the unit is. So how many grams is this? How many grams is an AMU? How many pounds or pounds mass is an AMU, right? You have no idea. Okay, now, but why define the AMU this way? Why is the AMU equal to 1/12 the mass of a carbon-12 atom? Well, why they chose carbon-12 as the standard relative atomic mass reference is because it's a stable and abundant isotope. Okay, that's why they chose carbon-12, but now why 1/12 of the mass of carbon-12? What's that about? Well, because if you define the AMU that way, then what happens is we know that, so at the time they could compare the masses of the proton and the neutron to get a relative mass between the proton and the neutron, and they knew that the masses of protons and neutrons were very, very close. Not exactly the same, but very, very close. If we look here, it's not until you get to this third decimal place in scientific notation that you start to get a deviation in the masses between protons and neutrons. And so with that, what that means is, so we also know that the electron mass is significantly smaller than the proton and the neutron mass, about 2,000 times smaller. So the vast majority of the entire weight of any atom is going to be contained within the nucleus, the protons and the neutrons. Then here's a carbon-12 atom. If an AMU is 1/12 the mass of a carbon-12 atom, then that means that the mass of a proton and the mass of a neutron are both going to be very close to 1 AMU. Not exactly, but very close. And that's what we see here. It isn't until the third decimal place that the masses of the protons and neutrons deviate from 1. So that's why the AMU is defined that way. The building blocks of all matter in the entire universe are protons, neutrons, and electrons. Well, in terms of mass, the electron is negligible compared to the proton and the neutron. So why not define a mass unit for atomic-sized particles to where 1 unit is as close as you can get to the mass of a proton and a neutron? Okay, great. Now, if we take a look at this table, though, you might notice something that's a little bit confusing here. So, okay, here's a carbon-12 atom. And so, all right, by definition, if we take the mass of 6 protons, 6 neutrons, and 6 electrons and add all of that up, we should get exactly 12 AMU. Because the AMU is still, if from a precise, exact standpoint, the AMU it's the entire carbon-12 atom, including the electrons. So take the mass of 6 electrons in AMU, the mass of 6 protons, the mass of 6 neutrons, add that up, it should be literally exactly 12 AMU. Okay, but if we look here, that's not the case. Just the mass of 6 protons and 6 neutrons is going to be greater than 12 AMU. Okay, well, what's happening here is there's going to be a difference. When you're thinking about masses of atomic-sized particles, in particular the particles associated with nucleuses of atoms, protons and neutrons, there's going to be a difference between a proton and a neutron on its own outside the nucleus compared to a proton or neutron within a nucleus, in which case they're referred to as nucleons. So the mass of a proton and a neutron as a nucleon within a nucleus is going to be different from the mass of a proton and a neutron or a neutron outside of a nucleus on its own, not as a nucleon. And the reason is because we've talked about how the nucleus of an atom is incomprehensibly dense, but then furthermore, it's unbalanced in terms of charge, so there's no negative charge neutralizing the protons. And so it's not only is it so dense, but there's an incredible amount of energy holding the nucleus together that we still don't fully understand. Okay, and this energy, right? This is nuclear energy, the most powerful energy that we're aware of in the universe. And so what happens is in nucleuses, mass energy interactions start to come into play, right? E is equal to mc squared. There's so much energy in the nucleus. And then combined with the fact that the masses are small as well, the masses of these particles, that you start to get these energy mass interactions to where some of the mass of protons and neutrons is manifested as energy in the nucleus. And so really, the more precise way you would say what the definition of the AMU is, if you're stating this definition from the perspective of the protons, neutrons, and electrons, is you would say that, okay, one AMU is equal to the mass of 6 protons and 6 neutrons as nucleons, all as nucleons contained within a nucleus, plus the mass of 6 electrons. So you have that total mass, 1/12 of that, exactly 1/12 of that. That is what one AMU is. Now, this can also be a little bit confusing because, so for example, if we think about, okay, here's the 3 different isotopes of hydrogen. Protium, where there's no neutron in the nucleus. Deuterium, where you have a single neutron in the nucleus. And tritium, where you have 2 neutrons in the nucleus. But it's hydrogen, so it's always 1 proton. And then if it's a neutral hydrogen atom, there's going to be 1 electron to neutralize that 1 proton. Okay, so you might think that, well, all right, here we've got, with deuterium, we've got a proton and a neutron pair as nucleons, and then a single electron, right? Okay, well, if we think about the carbon-12 atom, then, so how many proton-neutron pairs as nucleons do we have in this nucleus? Well, there's 6, right? There's 6 proton-neutron-nucleon pairs in the nucleus. And then there's 6 electrons. So, okay, 1/12 the mass of a carbon-12 atom. Maybe we can think about that as, okay, that's going to be each proton-neutron pair as nucleons, the mass of that pair together, plus the mass of a single electron, that absolutely is, in reference to the carbon-12 atom, that absolutely would be, so that would be what? 2 AMU, right? Because you've got 6 of those. You've got 6 proton-neutron-nucleon pairs plus a single electron. So, yeah, that would be 2 AMU. So there you go. You have 1 of those here. So this must be exactly 2 AMU, deuterium, the mass of a deuterium isotope. But that's not the case. Deuterium is slightly more than 2 AMU. And so what's going on here is that the difference is that this proton-neutron-nucleon pair isn't contained within a nucleus that has a total of 12 protons and neutrons, right? So you can't look at it that way. This pair here isn't at the same time interacting with a bunch of other protons and neutrons. And so because of that, one thing you want to keep in mind is when you look at the periodic table, we know that when we look at these atomic masses here of the different elements, you rarely see nice integer whole numbers for these atomic masses. And the typical reason why people would say that that's the case is because of the fact that these are atomic weights, right? These numbers correspond to the weighted average of all of the naturally occurring isotopes of the elements, which is why you don't get nice whole numbers, right? Which is why the atomic mass of carbon here is listed as 12.011. Okay, but then people have a tendency to think, though, that these decimals like this, in terms of atomic mass, are only associated with atomic weights, this averaging of the isotopes. But for example, if we had a periodic table that for each of the elements, it kind of had a box that showed all the isotopes, well, then with all the isotopes, we'd see nice whole number integers everywhere, because you're not you're not doing that average anymore. And that's actually not the case. Even with isotopes, you're going to see these non-integer decimals everywhere. There are some exceptions. So like oxygen 16 isotope is like 16.00, but I think even if you go past 2 decimal points, you'll start to see it's not an exact integer. Okay, but in a chart like that, yes, you would see that the carbon-12 isotope would be exactly 12 AMU. But even with the isotopes, looking at all of the different isotopes, you're going to see a bunch of non-integers as well. And it's for the reason that we just talked about, because all of the different isotopes of the different elements are going to have different total numbers of protons and neutrons in the nucleus. None of the isotopes of any of the other elements are going to have exactly 6 protons and 6 neutrons in the nucleus like carbon-12. And so it's going to have different energy to mass transfers based on E is equal to mc squared. And so you're just not going to have integers for the atomic masses. So keep that in mind. Okay, so with the AMU defined, and then with using techniques like mass spectrometry to determine relative masses between atomic-sized particles, you've got masses of atoms, so all the different isotopes of the different elements, masses of subatomic particles, masses of even molecules, defined in AMU. And so now with that, how do you bridge the gap between masses and even counts at the atomic size scale with masses and counts at the macro size scale, at the human size scale? Okay, well, this is done by, so a specific atomic sized particle is chosen, a specific particle, so it's the carbon-12 atom is chosen, the specific isotope of the carbon element, carbon-12, that's a unique atom, is chosen, okay? And then furthermore, a macro scale sized amount of this carbon-12 atom is chosen, okay? And that's going to be 12 grams. So a macro scale size amount, it's grams. We can measure grams. We have scales that measure grams, okay? And so with this pairing here, the idea is we want to use experimental techniques to count as precisely as possible how many carbon-12 atoms are in 12 grams of carbon-12. And once we have this number, this our best estimate for the count of the number of carbon-12 atoms in 12 grams of carbon-12, that number is going to be our bridge. We're going to use that number to bridge the gap between the atomic sized scale, masses at the atomic size scale, and counts at the atomic size scale with masses and counts at the human size scale. So that's the plan. Okay, now, but we could have used this idea of counting atomic sized particles with a certain amount of atomic sized particle. We could have chosen any specific atomic sized particle. We could have chosen oxygen 16 or maybe hydrogen, the protium isotope of hydrogen. Maybe we could have chosen an H2O molecule. And then we could have picked any amount here, 5 grams, 1 gram, 100 grams. So why this pairing here? Why the carbon-12 atom, and why 12 grams of it? Well, this is chosen on purpose to be in harmony with the definition of the AMU. So the AMU definition also uses carbon-12 as the reference. Okay, and then furthermore, one carbon-12 atom weighs 12 AMU, right? 1 AMU is defined to be 1/12 the mass of a carbon-12 atom, so a carbon-12 atom weighs 12 AMU. That's the reason. Making the statement that the number that we're going to use to bridge the gap between atomic size and macro size is going to be based on the number of carbon-12 atoms in 12 grams of carbon-12. Because that number is going to be lined up with the definition of the AMU, we're going to see how this is going to make the bridging of this gap as smooth as possible. It's not that we couldn't have chosen some other atom and some other amount in grams and still have been able to bridge that gap. We could have done that. It's just that the most ideal, the smoothest way to bridge this gap is counting the number of atomic-sized particles as shown here. And so, okay, using experimental techniques, scientists have determined that the number of carbon-12 atoms in 12 grams of carbon-12 is approximately this many carbon-12 atoms, 6.0221413 times 10 to the 23rd carbon-12 atoms. This is known as the mole, or also known as Avogadro's number. Now, if you're like me, the first thing you probably think when you see this number is, how could we possibly obtain this estimate to this level of precision, right? There's examples of how incomprehensibly tiny atoms are. These mind-blowing examples. So how could we possibly get this estimate to this level of precision, right? You've got 7 decimal places here. Well, okay, the first thing you want to note about this number is it's not as precise as it looks. Yes, it's still very precise and amazing, even mind-blowing how you could figure this out, even to this level of precision. But the level of precision is not as precise as it seems. What I mean is that, so no, this is not precise to 7 decimal places. This is scientific notation, right? If we move the decimal place to this last significant figure, then you're still left with 16 trailing zeros. So really what this number is saying is that we know that in 12 grams of carbon-12, there are 6.0221413 times 10 to the 23rd carbon-12 atoms, plus or minus 10 to the 16 carbon-12 atoms. The precision is 10 to the 16 carbon-12 atoms. That's still, it's not as precise as it sounds, right? That's a lot of carbon-12 atoms, 10 to the 16. Okay, but even so, though, it still is mind-blowing that we even know this. Like, how could we even know this? Well, we're going to talk about this in more detail in Chapter 5 when we study gases. Okay, but what we learn about gases, in particular gases that can be assumed to be behaving ideally, ideal gases, is that gases are significantly easier to study than the other phases of matter. And what we're going to learn is scientists have been able to use gases, to analyze properties of gases, to understand other more general properties of matter. So the 0 Kelvin, or 0 Rankine, absolute zero temperature, right? Which at that low of temperature, you're not going to have any gases. Everything's going to be condensed, right? But absolute zero was discovered, we're going to learn, from the study of gases, right? Avogadro's law. That's the same Avogadro. Applies to gases. The fact that if you have different types of gases, but they're all at the same pressure, temperature, and volume, then no matter what kinds of molecules these gases are made of, big, small, whatever, if the different gases are at the same pressure, temperature, and volume, then you must have the same number of molecules or atoms of the gases, right? So there you go. Now we're sort of talking about counts of individual gas molecules. Okay, but that is the mole, Avogadro's number. Now, something else to note about the mole, about this number, is that it is just a number. Okay, it's just a number in the same way that a dozen is just a number, or a pair is just a number. Yes, it does have a history. It does have a place that this number has a place that it came from. But so does the dozen, right? You can use the word dozen and without having to know the history of where the word came from. It's just 12 of whatever. A pair is just 2 of whatever. A mole is just this number of whatever. Okay, so it's important to remember that the mole is it's the same idea as like a dozen or a pair. Now, yes, we are going to use where the mole came from to do calculations in chemistry to bridge that gap between the atomic size scale and the macro size scale. Absolutely. However, in general, the mole is just a number. In the same way that a dozen is a number. You could have a dozen eggs. You could have a mole of eggs. It's a number. It's this amount of whatever you want. Okay, so now, but how does the mole allow us to bridge the gap with the atomic-sized scale? Well, okay, because of the way that the mole is defined, with the carbon-12 atom, the 12 grams being parallel to the definition of the AMU, because of the way it's defined, then if you have the mass of anything you want, anything that you define to be what's called a elementary entity. So you say, okay, I'm going to get the mass of an egg or a car or a proton or an H2O molecule or a big hydrocarbon molecule, whatever you want. You have the mass of something. You're saying, okay, I have this something here, and I'm going to get the mass of this something. Okay, if you have the mass of anything in AMU, you represent it in AMU. So a car weighs this many AMU, an egg weighs this many AMU, a proton weighs close to 1 AMU, an H2O molecule weighs whatever AMU, and oxygen 16 atom weighs 16 AMU. Then that value in AMU, if we think about the oxygen 16 isotope, okay, it weighs 16 AMU. Well, that value in AMU, because of the way that Avogadro's number is defined and the way the AMU is defined, this value is also going to be equal to what's called the molar mass of that elementary entity. Okay, with the molar mass, what the molar mass of something is, it's a property of something. Just like you have the mass of oxygen 16, you could also, another property is its molar mass. Okay, the molar mass is so it's going to be 16, the same quantity. It's the amount of mass, macro scale mass in grams that you need of this, to where then you have 1 mole of this. That's what molar mass is. So if you determine the weight of your vehicle, like a Forerunner in AMU, some big number in AMU, well, that's also going to be equal to, if you got that many number of grams of that vehicle, well, then that means you have 6.022 times 10 to the 23rd of that vehicle, right? So if we come to the periodic table, we know that all of these values are atomic weights of these elements. So there's the averaging of all the isotopes, but it's still the same concept. Because these values, like for phosphorus, because this value is in AMU, on average, the elemental phosphorus weighs this much AMU, well, then also that's going to be the molar mass of phosphorus. So if you collected this many grams of natural phosphorus with all the mixed in isotopes, then you know that you have 1 mole of phosphorus atoms with the same distribution of the isotopes. So if you have a mole of phosphorus, natural phosphorus atoms, then and 20% of those are known to be a certain phosphorus isotope, well, then 20% of that mole is going to be that phosphorus isotope, right? So again, if this is the mass on average of the phosphorus isotope atoms is this, but it's also a separate property because the way that the definitions are the mole is defined, it's also at the same time the molar mass of phosphorus. You get this many grams of phosphorus, then you must have a mole of phosphorus atoms. Okay, now, but in general, though, molar mass doesn't have to be, it can be in any mass unit. So we were just talking about grams per mole, but you could do kilograms per mole. You could do pounds mass per mole, slugs per mole, whatever. Tons per mole. Molar mass is just saying, look, how much mass of something do I need to accumulate to where then I know I must have 1 mole of that something, right? How many tons of Forerunners do I need before I know that, okay, I'm going to have 6.022 times 10 to the 23rd forerunners, right? That's in general what molar mass means. It doesn't have to be in grams. However, with that parallel between the AMU mass of something, that quantity being exactly equal to the quantity of the molar mass, that's going to be in terms of grams per mole, because this is grams. But you could get the molar mass of a vehicle. I mean, you would never use molar masses of vehicles. That's just I'm just using that as an example to give you some intuition of the idea of molar mass. The whole purpose of molar mass is atomic size scale particles, but you could get the molar mass hypothetically of a forerunner in grams per mole, but then convert grams to tons to make it more realistic. You really need to use something like megatons or even a huger unit than that to make it kind of realistic. Okay, but we can see where this comes from. We can see more directly where this comes from, why the mass of anything in AMU is going to be equal to the molar mass in grams per mole of that something. So, okay, if we think about the definition of the mole, all right, if we've got, so a carbon-12 atom has a mass of 12 AMU by definition, okay? Now, if we take a mole of these, right, multiply 12 by the mole, now we've got a mole of carbon-12 atoms, right? Which this is, so 12 times Avogadro's number is going to give us the mass in AMU of Avogadro's number of carbon-12 atoms, right? Well, we know that's 12 grams, right? So from here, just from this equation, we can get a conversion factor, a direct conversion factor from AMU to grams, right? We have Avogadro's number, just plug that in here. So 12 times Avogadro's number, that many AMU is equal to this many grams. And so there you go. You have 1 AMU is equal to this many grams, or you could divide both sides by this and get 1 gram is equal to this many AMU. Okay, and so there's really the direct bridge to the atomic sized scale in terms of masses. The big question is, okay, in AMU, how many grams is that? Right? And now with grams, we can convert grams to any mass unit we want easily. Other mass unit, kilograms, tons, slugs, whatever. So now we've officially got that bridge between masses at the atomic scale and the macro scale. Okay, but we can see, though, how if we wanted to see, if we had Avogadro's number of oxygen-16 atoms, then how many grams would that be? So that would be the molar mass, right? If we have Avogadro's number of oxygen-16 atoms, how many grams is that? Then we have the molar mass. Well, okay, we want to convert this. This 12 AMU needs to be 16 AMU, right? That's the mass in AMU of an oxygen-16 atom. So we could multiply this by 4/3 to now have 16 AMU, but to not change the equation, we multiply this by 4/3. Well, this is 12 and this is 12. You're going to get 16 on this side times Avogadro's number is equal to 16 grams. You see, that's the reason why it's based on the way it's defined. If you have the mass of anything in AMU, anything that you're saying is an elementary entity, an egg, whatever, then on the other side of this equation, based on Avogadro's number, on the other side of this equation in grams, you're going to have that same quantity. You see? And so that's Avogadro's number. That's the mole and where it comes from and how we use it to relate masses and counts at the atomic angstrom size scale and the macro scale, human size scale.